Okay. So next part is to show you another one. This is the last application I showed on version autoencoder, which is Sketch RN, which is to transform sketch images into embedding. This is also a Google project. Sequence-to-sequence autoencoder with variational inference. So it's a combination of variational encoder and LSTM encoder. Because they decompose each picture into a sequence of motor actions controlling a pen. Then you can feed this into LSTM. And you can do arithmetic operations like a peak plus a pad minus a pad body, which is the minus body. So this minus body is the peak pad. So this all makes sense. They verify that. Yeah. So this is like word embedding. They also did a smooth thing. So you randomly pick two human inputs and you can smoothly transition from one to another. This way you can do creative things. You can let small kids draw two pictures and see how they kind of how one can transfer one to another. So this is one application they claim. Yeah, they could also do something like this. If you draw something wrong, like a pig shouldn't have that many legs, and this will correct it. This may prohibit some creative.
The data available?
Yeah. You can read
the data available.
The data I'm not sure, but the application itself, I believe so. So you can try it. Usually, I think people don't. Big companies they do not want to do that, but you can see that. Okay, so at a research level, I think the question is how to ensure that. The way is to let's first start with this implementation level. You generate rather than generate the coding directly, you generate the mean and the variance of the Gaussian distribution. That is done for every element of the embedding. And then you want to sample from this Gaussian distribution because you want to feed the sample version to the decoder. Like here, you map it to here, and then you add some slight variance. You map this point to here, to here. You want to sample this. How to sample this? You do a random number generator according to Gaussian distribution. So you generate some standard Gaussian noise, and then multiply by the variance and plus the mean to shift this Gaussian to something here. So essentially, what this does is you want to pick a random point according to the mean and variance, and the way is to use a random Gaussian. This way you can backpropagate easily. This thing is the random part, making this probabilistic encoder and decoder. So it produces different things even after you train. Even after this training is done. At the inference stage, you will still do the Gaussian noise added and gathered. You could not do it. You could just get rid of it, but they claim that it's fine to still use Gaussian noise. Because this way, you could do generative modeling. You could pick any point here, any point. You could just randomly pick a point, or you could pick a point according to some existing point. Either way, you can generate new data. So that is implementation level. And it's not enough to simply sample it. They also have an additional loss function to enforce the Gaussian distribution. So they assume the prior distribution of the latent variable z, which is the coding here, pz, to be Gaussian. And they encourage the learned posterior q of zx. I'll explain in detail. So they encourage the learned posterior to be similar to pz through an additional loss term measuring the chiral divergence, which boils down to this form, only involving sigma and mu. So only involving sigma mu, you will get that. Kind of interesting, right? So, but we don't have I don't have enough background knowledge on variational Bayesian inference. So when I read this paper in 2013, I can get the basic part. But for every mathematical derivation, I don't have time to follow exactly. But what I can show you is that you have a probabilistic encoder and positive decoder, and by approximating this intractable posterior, you can derive the final loss term here. So it's all I can think of it as just a mathematical way to derive the loss function. But as implementation level, you can just use it. At the research level, of course, we need to understand everything here. So if you want to pause here, we can talk about it a little more. But anyway, let's talk about it a little bit more. So this is a probabilistic graphical model. You have your data x, you have a latent variable z. You want to infer what is the latent variable for every data point. So you have a dashed arrow, which just means the probabilistic encoder, which is a recognition model. They call it recognition model because they try to recognize what generates X. This is this direction. And it's controlled by some learnable parameter phi, which is essentially your encoder phi. And theta controls the decoding part, which is above, which is how you transform latent code Z to the original input X. That is the high level idea I can understand.
But the way you join there, the phi and the theta are given, or they have to be learned?
They have to be learned phi.
Right.
So phi is the variational approximation.
Mm-hmm.
Yeah.
How to learn that?
Through backpropagation, that's the implementation level through this. Yeah. Because neural network is just that way to approximate functions. And phi can be think of as parameter of that particular function q. To learn that q, you do backpropagation, update phi to get the q. That is the idea. And why do we have this complicated math? Because this is intractable. They claim that to estimate the true posterior, you need to integrate over all the possible latent code. And that is intractable. That's why they come up with something called variational lower bound. Okay. Actually, Zoe is very interested in that part, I think. Maybe sometime we'll consult with, ask for help from him. But anyway, this is the math part. So do you have any comments or questions? Okay, if not, then we can move on. It's good enough, but something happened in 2014. Does anyone know that? It's the invention of GAN, right? So then in 2015, immediately Ian Goodfellow, along with other people, of course, came up with this thing called adversarial autoencoders, which combines VAE with GAN, essentially. So we'll also look at that. That is something I can explain more in detail, actually, because GAN is kind of more intuitive than mathematical in some sense compared to variational Bayesian inference. So here, I think I can explain it this way. So the motivation is that if you have another Gaussian, if you want to enforce another prior, for example, if you want to make it non-Gaussian, if you want to make it an arbitrary prior, you would have to derive this loss function again. Right? You would go through this math to derive this loss function. However, you want to match to arbitrary prior, and you don't want to derive that every time for every prior. So that's the motivation, one of the motivations. So how to do it? How do you match one distribution to another distribution using GAN? Right? That is their Goodfellow solution. So go back to this picture representation. So Ian Goodfellow, essentially they use, so this is the original one. So this is the original model, VAE. You have the encoder, you have the decoder. And here, you have a latent embedding here. You have a KL divergence measuring the distribution and the true distribution part, the prior distribution, which is what you want to enforce. And now you just make it again, rather than creating a KL divergence, you have a GAN loss. This loss function is the same as GAN. If you're not sure, you can look at the GAN paper. So it's adversarial cost for distinguishing positive samples, which is what you want to enforce. Could be Gaussian, could be anything. As long as you can sample from it, it's fine. It doesn't have to have a mathematical closed form expression. So that's the advantage of this paper. Very clear? Do you have any questions? And you can design arbitrary prior like this. Even something like a Swiss roll, something like this, which is kind of cool, I think. As long as you can sample from it, you can get a good result. Right? The practical power, the ability of GAN to generate real quality example is why it works so well. That's the insight. GAN is a good tool, and then they use it. So here, what they do is that you could feed in some label. For example, for each MNIST image, you know its label is 1 or 2 or 3. So you feed a one hot vector representing its label to here. That helps the GAN to better reconstruct the input and give it a better latent representation. This is called semi-supervised learning because using the label in this part. They claim they just explain the Wi-Fi that the result is better. Right? Do you have any comments on this one? Essentially, you have 0 to 9, 10 categories. And this case, they enforce the Swiss roll distribution. Okay, you can design arbitrary ones. And we're almost the end. That's good. So this one is this is Wasserstein autoencoder. So motivation is quite clear in this paper. This paper is one of the best ones in ICR this year. So variational autoencoder has a lot of advantages. For example, it is theoretically very elegant. The variational based inference is very elegant in many people's perspective. Second, it has very stable training compared to GAN, which is hard to train. You need sometimes black magic to play this game well. Right? So that is the one disadvantage of GAN. Another advantage of VAE is that it has a nice encoder and decoder architecture. Right? But in GAN, you don't have encoder. You only have a decoder or generator, which transforms some noise into fake example. And you have a discriminator, which discriminates between the fake example and the real example. That's that. You want to somehow have encoder. That's their claim. They claim this better. And next, VAE has nice latent manifold structure that we saw before. Either some nice clusters or something even better. It has some disadvantage. The one big one is it tends to generate blurry samples. I talked this with some of my colleagues, and he said, not always true. Sometimes this is more like experimental thing. Right? This author claimed that sometimes it's blurry. Okay, and it seems very good. But GAN has a lot of, GAN can address that because GAN has good visual quality of images. GAN also has a problem of mode collapse, which means that the pictures that GAN generates more or less similar to each other. And also GAN uses JS divergence in its essence. So mathematically, they prove that GAN, under some conditions, is equivalent to minimizing the JS divergence, which has worse property than what they claim to be Wasserstein distance, which you can see more details in this paper. I did another presentation last quarter on this one. Essentially, Wasserstein has better property. That's the takeaway point from that one. So again, so you can visualize it this way. GAN creates some fake image from a noise distribution, and then they send the fake image as a negative sample to a discriminator. This is a real example. So what they send is the data in the data space, not something from the latent space. And what they want to adversarial autoencoder does is to use the latent code and the latent representation as the input to the discriminator, rather than the real data. And that's AAE. And what VAE does is a generalization of this idea by using Wasserstein distance to measure the difference between the model and the target distributions. Do you have any comments? Okay. Actually, that's one more thing before we finish this one. Is again, so this is a very good intuition for VAE. This is the data space X. This is the latent space Z. You are trying to minimize the reconstruction error. You first map it to latent space, and then map it back. For every data point, you do this. And you minimize the difference between this one and this one and this one. Because in this case, you random sample. Once you map it to here, and here, you take a random sample, right? The random sample could be this guy, and you map it here, so you minimize their difference. That's what VAE does. And they enforce this Gaussian distribution, like a circle, like a set of circles. And here in Wasserstein reconstruction, as you see here, they minimize the reconstruction error between the actual data, because they don't have this. They claim that they don't need this probabilistic encoder and decoder. They could use deterministic encoder and decoder, which means that this one will be mapped to the real one here, not the sampled one here. That's one advantage. One more advantage. Deterministically, it maps to here. deterministically maps back to here, not some random sample and then map it back. That is one key. If you think about it, this is a really key contribution. This is open reveal. One of the anonymous reviewer mentioned this is a key contribution. You can use deterministic autoencoder rather than randomly sample and then map it to here. And they also claim that they have better latent space structure, right? Because here their claim is that there could be intersections between different clusters. Like for this data point, you do a Gaussian. For this one, you do another Gaussian. There could be intersections, making the final latent space not that nice, not nicely separated compared to this one. That's their claim. And they experimentally verify that again.
Can you explain in that first example, the three yellow balls are mapping to the same square box?
Why, right?
Yeah.
Okay, so let me explain again. So that actually goes back to the definition of VAE, or a key thing in VAE is here. Each time when you feed into a decoder, you randomly sample something according to the distribution you generated. You have a Gaussian noise, making it non-deterministic, making it probabilistic. Okay. And here, and that's why in this case, let's go back to this example. In this case, they are mapped to different embeddings. But because you take this Gaussian distribution, these are very close, do you agree? These two things are very good. This comes from, okay, let's think. This is just, okay, so this maps to here. But you could, by taking a Gaussian, you could end up with this guy, do you agree? And then you send this to the decoder. And that's why you deconstruct this. And for another one, although it should be mapped to here, but because of the non-determinist sampling, it's also mapped to here. That's one specific case. Okay. And any other questions? Yeah, so that is the research frontier. That is the latest, I would say, latest advancement. There have been a lot of, they say, a flurry of other research activity. They use the word flurry, trying to combine these two things, VE and GAN, in a principled way. And they claim they are the latest and they are the best. So if you are interested, you can read more. They have a very nice tutorial in the appendix explaining the difference between them very well. And they show why it's a generalization of AAE. So yeah, this is a very hot research area. At the final, maybe 5 minutes, I want to briefly talk about autoencoders for graphs. Graphs are different, right? First of all, fundamentally, is there any smooth linear interpolations between graphs? The answer is yes. So this guy's the latest paper called Graph VAE. They are applying the same rational encoder on graphs, and they find that there's linear interpolation between two graphs. This is a chemical compound. This is a graph. There's another chemical molecule, another compound, and they draw a line, and then they visualize everything in the middle. Something is invalid, like this one. It's not chemically valid. So this is the latest research work on graph VAE.
But they still generate anyway.
Yeah, they still generate. It's just
so
something.
By adding some constraints,
Yeah,
something
of course.
To make sure the thing they generate are
Oh, the chemical invalid. That's a good research direction. Yeah, we could discuss more later. It's not there yet, I would say. So yeah, arithmetic options, I haven't seen any paper on that. So maybe you could say two triangles, you add the embeddings and you get the embedding for a rectangle, because two triangles somehow in certain way they could compose that. So this is another research direction. Is there arithmetic operation? Next difficulty is graph is composed of correlated substructures. If you think about this, pixels are atomic, you can't break it down. But pixels can form patterns, and patterns form images. Words form phrases, form sentences, and then form paragraphs and documents. Nodes in graph form substructure in graphs. And you can think of transfer learning, how to use one data set and apply it to another. This is just possible research direction I want to point out here. Not necessarily something people have done, just some thoughts. The third thing is that graph can be different sizes, and there's no order between different neighbors of a particular node. So these are all things that make this hard problem. And how to detect substructures. For image, we can use CNN. When I have convolutional autoencoder, we saw before. For graph, we can use graph convolutional layers. That's what this paper does. This is what this paper does. They use graph convolutional networks. Some people treat graph as sequences and random blocks. I think this philosophically, they use the deconstruction view. They break down graph into different substructures. It's similar to parse sentences into trees rather than feeding the sentence directly as that. But this is a valid philosophical thing, I think, a point of view. Decompose graph into substructure. For example, sequence. For example, equal size subgraphs. Maybe for each graph we decompose into a 3-node graph, a bunch of 3-node graphs, and feed them into some detection, some neural networks. Those are just possible directions that we can explore. Also, it's generative. This model can generate new, as you see. Although it's invalid, but they can still somehow generate new molecules.
I feel like people are somehow thinking about how to add constraints
Right.
so that actually, in the end, what you learn.
That is not the same architecture. You are right.
I know. That could be better capture the real hidden
parameter. Right.
substructure, right?
Let me.
Because otherwise,
Yeah.
if you're generating something not fitted, chemically
Right.
valid, then that means actually you're not interpreting those things, right?
Right.
You're violating something, right?
Yeah, valid.
That,
You remember the smell string I told you once?
yeah.
People somehow linearize each chemical compound into some
Right, into a string.
carbons, into a string, and then they first transform the string to some parse tree. Use some language theory from computer science. So they essentially enforce the grammar rule through first transforming this into a string, and then from string to some tree representation, and you feed that tree into the variation autoencoder. That is what people have done. But that is domain specific. That is valid for chemical compounds and may not valid for general graphs with some constraints from general constraints. It could be hard to do that. But these are all valid possible future directions. That pretty much ends we will have 1 minute. Do you have any questions?
I have a request.
Yeah.
Can you go to the roadmap slide?
Yes. Okay.
This one.
Okay.
Now that 1, 2, 3, 4, 5, 6, 7, 8, we have learned 8 different encoding schemes.
Okay.
Can you tell me what are the neural network structure and what are the loss function? So I have a data, right? And now I want to come up with the encoding using, let's say, static convolutional autoencoder.
Okay.
Can you tell me the neural network structure and the loss function to somehow train it on that using that particular scheme? What is
So you want to do it now or do it later, or what do you mean?
just
Or
very,
from
very,
slides?
very, very quick summary. So
summary.
sparse
Okay.
autoencoder.
Sparse autoencoder. Okay, so if you recall, it has a sparse penalty. We discussed this a lot, right? KL divergence. That is just simple, just one loss term. For denoising, you don't have efficient loss term. You only add Gaussian noise after the inputs, and you reconstruct the same input.
So we know add the input to the add the noise to the input. To the input. Okay.
Right.
Yeah.
For contractive autoencoders, you add a loss term minimizing the absolute value or something like that for the derivative.
So we don't use the typical loss function. We just use that loss function. We add it to the typical.
Always add it.
We
Because
add it
there are
to-
two opposing
see.
goals.
I
One
see.
is reconstructing, one is regularizing. This autoencoder is this is just a general way because you can replace dense layer with convolution layer for pretty much everywhere. If you want to do that, you could, as long as you have a reason. So loss function, it doesn't care
change,
about that.
right,
Yeah.
right.
This one recursive. This is a structure. This is like loss function could be the same as before, but you do it recursively as a meta level. You sort of treat your sentence as a tree, and
Right,
then
right.
you do it recursively.
Right.
7. Vibrational autoencoder is like you can generate new data, but if you don't want to generate data at the basic level, infantation level, you just add the Gaussian noise. After you get the hidden code, you treat the hidden code as two things: the mean and Gaussian variance, and you sample it. And because this enforcing Gaussian prior thing, you arrive a new additional loss term, which is there I showed
Hold
before.
on. So variational autoencoder is different from denoising because we are adding the noise at the
By the
hidden
hidden
layer.
layer, not from the
Right.
input layer.
But when we get the encoding,
Right.
we don't have the mu and we don't have the sigma. So where do you get the mu and where do you get the
Mu
sigma?
and sigma are the output of the coding. So they are the coding. They are not the coding themselves, but they are the output of the encoder.
So the output of the encoding
Are the
is mu
mean
and
the
sigma. Oh.
But the actual coding is from the mu and sigma. It's sampled from mu and
I
sigma.
see.
You add the Gaussian node to sample it. And the adversarial autoencoders. Adversarial autoencoders, you use essentially this is more complicated. Now you use to GAN training. You need to incorporate GAN. So hard to say in one sentence, but just use
Maybe
GAN.
I can say
Yeah.
we generate whatever hidden vector
Yeah,
space.
right.
We generate a random number of random vector, and
Right.
then we pass it through the
discriminator.
generator,
Or generator.
and then we pass it through the discriminator, and then we check whether that is correct or
Remember,
incorrect.
yeah. Only thing I want to mention that you don't have a decoder. That's one thing you can. For this part, for the it's hard to without example. For this one, you don't feed the real data into discriminator. You feed
Right.
the hidden representation.
Hidden rate, right.
That is important.
Right.
Okay, you are right. Okay, so and the last one, Wasser's test, is a generalization of
Right, right.
with
Just-
some. So it has other use case. You should read it. Yeah.
Okay, good.
Okay. Thank you very much.
Thank you.
Cheng will do that 2 weeks later, I think, right?
Next week.
Next week, not for now, no. But 2 weeks later, we will have Cheng. Thank you.
Yeah. Last time.